5. Really, you recall that the bright spots are kind of large areas, but I thought we wouldn't fool with that. I gave some numbers just to represent as though you had taken a meter stick and just simply laid it down sort of arbitrarily like this and then started to record the positions. And the positions that I said that you got were, where are they? Here they are. 39.30 centimeters. What's next? 40.39. 4140. 4230. And finally, 4333 as the positions of those 5 spots. Now, by the way, one of the assumptions you really needed to make was that the center spot was indeed the bright central maximum. So I'd be looking for that to see if anybody mentioned that. Yes?
Do you really have to?
Yes.
Why?
You'll see when you do other experiments, but sometimes things don't get lined up perfectly and you'll get more visible spots on one side than you do on the other. It doesn't always, the pattern doesn't always come out symmetric unless the alignment of the experiment is perfect. You'll see it in the later experiments. Yes?
We have to assume it's monochromatic light.
We also have to assume it's monochromatic light. But anyway, this would then be, the distance from here to here is 2, I'm going to call this y1, and this distance is 2y2, meaning, of course, well, let me put the formula down, but meaning, of course, m equals 1 and m equals 2. So our formula, oh, and the last thing before I put the strategy down, the last thing is, I told you about the slits. So here would be one slit, and here the other slit, like this. This is the dark area here, this is the dark area. So you're looking at these slit positions, and to see if you use the linear measure microscope, I only gave you numbers without units. The numbers I gave were 20.51, so 20.51, 20.39, 20.05, and finally 19.93. Of course, all of these measurements were in what? Do you remember? Millimeters. Yeah. So now it's time to write down the strategy. We've got some kind of data sitting here like this. Now let's write down the strategy. D was equal to 7 meters. And the fundamental formula starts out like this. D sine theta equals m lambda. As soon as you write that down, you know what else you need to assume? That theta small. This formula breaks down if theta gets very large. But if theta is small, this formula works. D sine theta equals m lambda is the formula. And of course, we then went to sine of theta. Well, we are looking at this triangle. Let me try to draw this relatively accurately like this. So in this triangle, the sine of theta is y divided by d squared plus y squared under the square root like this. So finally, lambda equals d sine theta. No, I just replaced the sine of theta. D times the sine of theta, which is y over d squared plus y squared, divided by m. And now the next thing we have to do is work out some of these numbers. That is for m equals 1, we have to get this spacing by a simple subtraction, divide it in half, and we've got a y value then for here and here. The d value, of course, some of you actually worked out 3 different d's, a minimum, a maximum, and the average, which is really good. I won't count you down if you did not do that. The d value that you would probably use to get an approximate answer would be from center to center. That would be the d, little d value like that. So again, you'd have to find the center through the appropriate subtraction, find the center here, and find the center there. Now, would you do me a favor? Would you use your calculators right now? And first tell me where the center is between these two, and then tell me what the spacing is. So the first thing I'd like you to do is give me the dimension of the center of each one of these slits, please. Just do that simple subtraction. Where is the center of each slit, please? Call this the first slit, the second slit. 19.99 for the first one. 19.99. Anybody get the second one? 20.05. 0.45? 20.45. Therefore, the slit spacing between those two is the subtraction, which is what? 0.46? 0.46 millimeters? So we now have a value for D. D is 0.46. Mike, do this subtraction for me, please, and tell me what Y1 is. Y1 is, of course, this difference divided in half. So 1.98. 1.99 divided in half. Is that what it is?
0.955.
0.955 centimeters. What else do we have? We have big D, which was 7 meters. And we're now ready to calculate, aren't we? So, what I'm going to call lambda 1 is going to be D, which is 0.46 millimeters, times, I don't think I have enough room. I think you'll forgive me for erasing this now. Y, which is 7 meters, divided by, and you really should write it as 7 meters squared plus, what was Y? Here it is, 0.955 centimeters squared under the square root, all divided by, where am I? M, which is 1.
Why is it 7 meters?
The top.
The top is wrong.
Top line.
Top Y is wrong. I just wanted to see if you were paying attention. Let me see. Y is which dimension? Y is this dimension. Okay, now Y is the spacing between. Okay, so that was 0.955 centimeters, like that. And then we divide by M, which is 1, so we really shouldn't put it there. Clearly we have, meters, square root, meters squared. So, obviously this will go with one of those. We're going to end up in meters. And 0.46 times 0.955 times 10 to the minus 5 divided by, I don't know what this is, 49 plus 0.955, 10 to the minus 2 squared under the square root. That's going to be all in meters. I hope that helps it, makes it easier for you to calculate. Would you now calculate this value and give me the answer in meters? 0.46. 10 to the minus 3, 10 to the minus 2 is 10 to the minus 5. 49, that one I can do. This I cannot square in my head.
6.28
6.28, 10 to the minus 7, I think you said.
That's right.
Anybody else get that? 2, 3, 4, okay. Looks pretty good. But of course I asked for it in angstroms, so you really should make it 10 to the minus 10th meters, shouldn't you? You do that by simply moving that 3 more places, 6280 times 10 to the minus 10 meters. So 6280 angstrom units is the answer. You get when you use just the center of the slots. Some of you went to the business of calculating a minimum wavelength and a maximum wavelength depending on the outer limits of the splits, and then quoted the value plus or minus the range. That's really a good thing to do. That's above and beyond the call of duty. All right, so any questions? Comments, cares, or concerns?
Why is M1?
Because we were using the spacing between bright central maximum, we use the space between here and here. That's when M equals 1. That's the first time you get a fringe on each side of the bright central maximum.
Okay.
One person quite nicely then checked by measuring Y2 and putting M equals 2. Where it is. Putting M equals 2 and putting in the second value for Y by getting this distance from here to here, which is nice, which was really nice. I tried to make it consistent so that you would get the same value either way and somebody got the same value both ways.
Couldn't you also just take the distance between the dots?
Yes, you can theoretically, but it's much more accurate when you do the experiment. You'll find, like we were saying a moment ago about your earlier question, the picture doesn't always come out to be exactly symmetric. So, you know, this might be a little bit small and this might be a little bit big, and the average distance is that divided
Well,
by 2.
we take all the distance between the dots and then average them out. Yeah.
Take the distance between the dots and average them out. That would also work. I tried to make it so that they were, I think they were pretty regularly spaced, weren't they? I don't remember if they were exactly spaced properly. All right. Any other good stuff? Any other questions? Yes.
You took not the bright spot in the middle, but say the 2 on the leftmost, and the distance between them, would your end value still be 1?
It would work, but it shouldn't. It would work as long as the M value, as long as the theta value is still quite small. The difference is so small you'd never notice it. So, you know, it's a lucky yes, is my answer. Luckily, and I designed it that way, but it's not really proper. Good questions. Anything else? All right. What was the fundamental purpose of Young's experiment? Not your lab, but Young's experiment. When Young did it, what was the fundamental purpose? That's right. To show that light is a wave, and then secondarily to measure the wavelength. Okay, good. Now, let's go to, let me check my notes before we go to today's lecture and see if there was anything else I wanted to comment on. Yes, we will meet for lab today, 2:30, isn't it?
Yeah.
So far, for some reason I wanted to reference page 533. Oh, I remember. Yeah, page 533, here's where we talk about the electromagnetic spectrum, and I don't know if I mentioned this before, but typically, when I use the word light, for example, if I say the speed of light in a vacuum is 3 times 10 to the 8 meters per second, I actually mean any form of electromagnetic radiation, not strictly visible light. If I want to restrict the conversation to visible light, then I always put that word in there. I say visible light. But if I don't do that, I mean all electromagnetic radiation. And on this page, we talked a little bit about how Newton discovered what he first discovered about light, that white light is an equal mixture of all colors, and that the prism separates the colors of light. And then I thought it was kind of cute on the next page, pages 534 and 535, they talk a little bit about measuring the speed of light. Light is very fast. I just gave you the value, and I'm sure you know it. The speed of light, in this class from now on, I'm going to reserve small case c to be the speed of light, 3 times 10 to the 8th meters per second. That sounds fast, and it is. That's, in roadside terms, that's 186,000 miles per second. 7, almost 8 times around the equator of the Earth per second. Light is very fast. Now you can understand why, when Galileo tried to measure the speed of light, he failed. What he did was, he and a friend stood on 2 hilltops several kilometers apart with a lantern with a shutter. And Galileo and his friend made this deal. He said, I will open the shutter as soon as you see my light. You open your shutter. As soon as I see your light return, I'll measure the time interval. By knowing the distance traveled and the time required, I should be able to calculate the speed of light. When they did the experiment, and that is, Galileo opened the shutter and started the timer. When he saw the light return, he stopped the timer, and he got about a half a second. And he knew immediately, what did he just measure? What is it that you suppose it takes? Half a second. Reaction time. Yeah, he just measured reaction time. All he knew, and he was quite correct, is that light is incredibly fast. It's so fast that all I did is human reaction time. So the next illustration on the next page shows another way of measuring the speed of light, and that is a telescope. When light enters a telescope, and the telescope is on a spinning Earth, of course it enters the telescope at the top, and it takes a short period of time to come down the telescope. And if you're pointed directly at the star when the light enters, by the time the light gets to the bottom of the telescope, it misses the mirror. So you have to tilt the telescope in advance of the star, and the angle measures the time it takes for the light to travel down the telescope. Telescopes are phenomenally accurate instruments. Using this technique, we were able to get the speed of light. By the way, I always like to think about it like this. You know how fast light is? It goes that far in a nanosecond. Light travels about a foot a nanosecond. That's the speed of light. And so, now that we have telescopes so incredibly sensitive, we can measure the speed of light through the length of a telescope. It's just kind of interesting. These 2 pages are just kind of an interesting way of measuring the speed of light, and I wanted to bring that up. Now, I want to make a definition that we'll be using later on, either today or on Wednesday, and that is a number which we will call n. Definition. N will simply be defined as the speed of light in a vacuum divided by the speed of light in a medium. Yes, light slows down when it enters a transparent medium. A very small slow. When light enters air, when it comes from outer space and gets into the air, it slows down by about 0.3%. Trivial.
Which one's the vacuum, what was the medium?
C is the speed of light in a vacuum. And V is the speed of light in whatever medium. When light enters glass, it slows down by about 30%. That's pretty significant. So this is called the index of refraction, N. And as you can tell, for any medium, any transparent medium, N will always be larger than 1. The only time N equals 1 is in a vacuum. In a vacuum where the speed of light is not disturbed. Otherwise, oh, it says C table 16.3, page 537. Oh, there it is. On page 537, they give us some indices of refraction. And you'll notice that the gases are pretty small changes. The index of refraction for helium, 1.40 and a 3.6. But when you go over to the other side where there's liquids, for example, with the speed of light in water, 1.33, alcohol, 1.36, go down to benzene, the speed of light must be remarkably slower because N is 1.5. And then, of course, they have diamond. Diamond is the slowest thing I know. Light is slowed down in diamond more than any other substance. Notice that the speed of light in diamond must be remarkably slow because N is almost 2.5. So these indices of refraction have hidden in them the speed of light in that particular medium. So N is always just simply the speed of light in a vacuum divided by speed of light in a medium. By knowing the index of refraction, you can always get the speed of light in that particular medium. So let me start with that as just a definition, and then we'll be using that definition a little bit later. What I'd like to do now is change the subject just a little bit. Not really, but a little bit. I'm going to talk with you about the Doppler effect. And the interesting thing, the reason you're going to think I'm changing the subject is because I'm going to start with the Doppler effect in sound. And then we'll talk about the Doppler effect in light. The reason for that is because I think all of us here in this room, have heard the Doppler shift in sound before. And it's a little easier to analyze. And then once we have the Doppler shift figured out, then we can recast our solution into a light Doppler shift equation. But let's start with the Doppler shift in sound. What am I talking about? I think you've probably heard the Doppler shift before, but it goes like this. Imagine you're standing alongside of a long, straight road, and here comes your friend in a car. Your friend sees you and wishes to acknowledge you, but does not have time to stop. Therefore, as your friend drives by, they honk the horn and wave. And when they honk the horn and drive by, it sounds like this. Listen, because I practice. It sounds like this, doesn't it? It goes, beep. That's what it sounds like, huh? Pretty good. Don't you think? Yeah, that's the Doppler shift. What do you think? Do you think your friend has a little rheostat installed on his dashboard so that when he first sees you, he turns up the high frequency, and then as he drives by, he turns it down? No, of course not. This is a natural phenomenon. Whenever anything's approaching, beep, the pitch of the sound is high. Beep, and just as they pass, beep, the sound decays to a lower frequency, and then beep, it holds at the lower frequency as it recedes from you. This is a natural phenomenon. You can hear it in cars and all sorts of things. I think we've all heard the Doppler shift before. Many of you knew it by name. Some of you, well, you've heard it, but you didn't know the name of it. Well, that's the Doppler shift. And now what I'd like to do is talk with you a little bit about how that happens. Unfortunately, using the sound of a car horn is a little bit complicated. So I need a simpler sound, a sound that you can relate to. I know. We'll use the beautiful and melodious sound of my voice. What's going on? When I speak to you, in my throat, there are two vocal cords stretched tight. And when I blow air over them, they vibrate fore and aft at a frequency of about 400 cycles per second. I know, I've measured them. Each time the vocal cords come forward, they compress the air immediately in front of the vocal cords. That compressional zone is not stationary. That compressional zone moves as a wave front at about 330 meters per second. Up my throat, out of my mouth, and into the room. As that pressure front is moving forward like that, the vocal cords retract, making an area of low pressure. They come forward again, making another high pressure, low pressure, high pressure. They do that about 400 times per second. So out of my mouth, there are 400 pressure waves coming out, spreading out into the room, captured by your ear, funneled down to the tympanic membrane, the eardrum, which vibrates sympathetically at 400 cycles per second. 3 little bones carry that vibration into the liquid-filled semicircular canals deep in your ear. The liquid vibrates and stimulates little cilia, hair-like structures inside of your ear, which, when resonance hits, creates a small electrical signal. It goes back into the back part of your brain, and you say, ah, what a beautiful and melodious voice. That must be Dorio speaking. You recognize the sound of my voice.
Like you read that line.
You've read my mind. Now let's imagine what happens if I'm going to speak to her, but simultaneously I'm going to be walking towards her. Here's what happens. Here comes the first pressure wave. I'm starting to speak to her. The first pressure wave is on its way to her, but before I make the second pressure wave, I've moved forward a little bit. So the next one comes out closer than it should. And the next one, and the next one. As I walk towards her, I compress the waves. Hence, therefore, she will hear them at a frequency higher than I emit them. And of course, the same thing happens if I'm speaking with her and moving aft.
But if you're moving at a constant speed, wouldn't they all still be the same distance apart because they're being compressed the same amount? Or
They would all be the same distance apart. They would be compressed the same. Yes, they would all be the same distance apart, but all of them compressed.
so like
All right. It's a little bit like
You could
sit in a boat and throw a rock, and the waves go out. Okay. Now you're in the boat and you're moving with the waves. You throw a rock and you throw the next rock and you throw the next rock, so that each new wave that you make is closer. You're moving with the waves and you're throwing the rocks. Now imagine moving aft. I'm speaking with her and I'm moving aft. So here comes the first pressure wave that's on its way to her. Before I make the second pressure wave, I'm back here. And the third one and the fourth one. So they move at the same speed, but the wavelength has been stretched. She will hear a frequency lower than the frequency I emit. Ladies and gentlemen, that's all there is to the Doppler shift. I move towards her, I compress the waves, she hears a high frequency. I move aft, I stretch the waves, she hears a lower frequency. So naturally, of course, if I'm running along in this direction, as I'm going in this direction, I am actually getting closer to her right until now. And now I'm starting to recede from her. So as I approach, I will compress the waves that she hears. As I get right abeam her, there will be no Doppler shift at all. That will be the moment that she hears the perfect sound of my voice. And then, of course, the shift to longer wavelengths happen as I walk away from her. Our author has a beautiful picture of this sort of thing on your page 542. If you would kindly go to page 542. On page 542, we have two observers simply labeled as Observer 1 and Observer 2, O1 and O2. We have a source of sound, which is a bandsman playing what? A trumpet? And in the first illustration, figure 1621A, everybody's stationary. The trumpeter is just standing there and he's making these beautiful trumpet sounds. And they're moving out as spherical wave fronts. And as you can see, the wavelength enjoyed by both observers, her in front and him behind, will of course be the same wavelength. Now notice what happens when the bandsman is moving towards her and away from him. As he moves towards Observer 1 and away from Observer 2, Now, the first thing that's important is to look at the illustration, and that is, you see position A, small a there? That's where the opening of the horn was when he produced his first pressure wave, which is, of course, the largest pressure wave. Position B is where the horn was when the second wave was produced, which is the next smaller wave. And so on. A, B, C, and D are the locations of the horn from the first through the fourth wave fronts. So now you can see what's happening. You can see what we were talking about. As he moves towards her, observer number 1, the waveform gets compressed in his direction. Excuse me, in her direction. And for the gentleman behind, he's moving away from him, from observer number 2, the wavelengths get stretched. So this illustration is the best illustration, I think, just showing what the Doppler shift is doing. Each waveform is centered on the point where the horn was when it made that waveform. So let me just emphasize that point. When he makes the first, here he is at position, our author calls it little a, and he produced this wave. So of course this wave is symmetric. It's perfectly symmetric. It is centered on point A. Point B is where the horn was when it made this wave. So this wave, which is a smaller wave because it's the second wave, it hasn't been traveling as far. This wave is centered here, it has shifted a little bit, and that puts the whole waveform this way. That shifts this to a smaller wavelength and this to a larger wavelength. My picture is nowhere near as accurate as his, but that point is extremely important so that we can understand his Doppler shift formula. Now what our author wants to do is to describe the wavelength enjoyed by her, observer number 1, as the band moves towards her. And so what does he do? He says her wavelength, lambda, and let me write it down using exactly his notation, because some people get a little confused, and I want to be specific. He is very accurate about his notation, and I want to be specific about it so that the confusion won't happen. He starts out by saying this. He says that lambda, the wavelength enjoyed by observer number 1, is simply going to be the distance between the two wavefronts, which he calls x capital A minus x capital B. So in our illustration, does he label them? He really doesn't. He really doesn't label them, but x sub A is this position right there. That would be x sub A, and this would be position x sub B, like that. So the difference between those two x values is the wavelength. So he uses the capital A to represent these two positions, and the little a and b to represent these two positions. The capital A and B represents the positions of the wavefronts. The little a and b represents the positions of the horn when those wavefronts were produced. Okay, well, he goes on then to argue that R sub A minus, and then what he does is he puts down X sub B minus R sub B. And so what he's saying then is that, let me see if I got this just the way he wrote it. Yeah. Except I put a minus there instead of a plus. Why is it a plus? It is a plus, isn't it? That makes more sense to me. Why is it a plus? Because X sub B is the new position where the horn was when it produced the wave, and R sub B is how far the wave has traveled. So those two actually add together because they're both going in the same direction. Since he moved from A to B, then the center of the second wave is over here, moved forward a position X sub B. and R sub B is the size of the thing. So to measure where this thing is, you have to measure how big it is and how far it's moved. Does that make sense? Making all kinds of sense to me, but I'm looking around at you guys and I'm not sure it's making sense to you. You guys are okay with it?
Is R supposed to mean radius, receiver, what does it mean?
R is radius.
Radius?
Yeah.
Radius?
Of the wavefront. You'll see that in just a second, but yes. Radius. All right, so now, why did I put that down as that? I don't know. I'm going to correct this right now. Later on, the minus sign just magically turned to a plus sign on my notes. I don't know how I did that. All right, now let's try to put down what these things are. And it's kind of an interesting argument that I'm going to put up here. Watch this. I'm going to say that R sub A is VW times 2T. What do you suppose V with a subscript of W represents? That's correct, the speed of the wave. And then 2 times a capital T, what do you suppose that is?
Period.
2 times the period, you're right. Okay, so this represents how big RA is. The speed of the wave times the time that it had to travel from here to here. That's the radius. Now subtract from that XB, that's this distance right there, which he puts down as V sub E T. Now what do you suppose V sub E represents? Velocity of the entertainer. That's the speed with which he's moving. And T, of course, is 1 time period because it only takes him 1 period to get from position A to position B. That's what we're defining as those 2 positions. And then he adds to that R sub B, but R sub B is the same wave, so it travels at the same velocity. However, now it is 1 period later, so it only requires 1 T to travel to position B. So good. I think this has been the main sticking point for some people, and I think you guys got this. You got whatever your little term is in there, right? Everybody's happy with that? Now's the time to check.
And the velocity of the wavefront, that is the velocity or the speed of sound in
Yes.
the air, right?
Yes. Here and here, yes.
It doesn't make that very clear in here.
No. That's why I'm trying to make sure everybody's got all their questions answered now. Velocity of the entertainer, etc. Okay, well that's pretty good because it's real easy here, isn't it? 2 velocity wave T minus velocity entertainer T plus, minus velocity wave T. So of course it is T times the velocity of the wave minus the velocity of the entertainer. So now we've got the wavelength that she enjoys. And we can replace for the velocity of the wave, we can put down that the velocity of the wave is actually the wavelength, V naught, divided by the period T. So that's one way of replacing the velocity of the wave, is what's the original wavelength, what's the original period of the thing. So replacing that, putting in for T equals what? Lambda naught over VW. This is just a definition. This is how we're going to use the thing. So if we put that in right there, we now get the lambda that she enjoys is equal to lambda naught over VW times what? VW minus VE. So, of course, we have lambda naught times 1 minus VE over VW. And we have a Doppler formula to tell you the difference between the wavelength that she would measure and the wavelength emitted by our entertainer. So there's a Doppler formula that deals with the change in wavelength. Of course, in sound, we're not so used to actually seeing the waves and measuring wavelengths, but what we measure more conveniently is the pitch, the frequency that we hear or detect with the oscilloscope. So, what we'll do then is to simply put in place of wavelength lambda, that is the velocity of the wave divided by the frequency that we hear, and lambda naught is going to be, well, it's the same wave velocity, that doesn't change, but here's the fundamental frequency. So here's the wavelength emitted by the stationary observer, or the frequency that you hear if the observer was stationary relative to the sound source. And here are the shifted wavelengths and frequency. So if we put those in, of course, we get what? Lambda VW over F frequency equals lambda naught, which is VW over F naught times 1 minus VE over VW, like this. And then just simply solve this thing for F. So we put this up here, that up there, and we get F equals F naught divided by this thing, 1 minus VE over VW, like that. And we have a Doppler shift formula for the change in frequency. Whether you measure wavelength, which was this formula here, or frequency, which is that one there, we now have a way of predicting the Doppler shift, and it's determined strictly by the ratio of the velocity of the entertainer divided by the velocity of the wavelength. The speed of the observer divided by the speed of the wave in the medium. Color is to light precisely what pitch is to sound. Let me say that again. Color is to light precisely what pitch is to sound. Yes?
Before we move on, could you show us so there's no doubt, where's lambda naught and where's lambda on the picture right there?
This is lambda. Here to here. And lambda naught is on the previous picture, where nothing moves. This would be lambda naught, where nothing moves. And yes, he actually shows that. If you're on page 542, illustration A, lambda naught is the unshifted wavelength when nothing's moving. See it there? Okay. Hence, therefore, if I had a flashlight, now instead of speaking with her, let's imagine that I have a flashlight. I turn on a flashlight, I walk towards her. That's going to compress the light waves. Or I walk away from her, that's going to stretch the light waves. So the light that she sees will either be shifted towards shorter wavelengths or longer wavelengths. The common term that we use is to say that she observes blue shifted light. That doesn't mean that she sees blue light. But remember, blue is the shortest wavelengths that we can say short end of the spectrum as far as human eyes are concerned. So if we compress it, the light is all getting shorter wavelength, and they say it's blue shifted, headed towards the blue end of the spectrum. And conversely, this is called a red shift of light. The light that she sees is shifted towards the red end of the spectrum. Now, funny story, apparently it's true, but I wasn't there. Some years ago, a young lad got a traffic ticket for driving through a red light. He should have gotten a ticket for stupidity, because there was a four-way intersection traffic light, and the first one sitting there waiting for the light to turn green was a black and white, a cop car. And our young friend comes towards it, and the light turns red, and he drives right on through. Idiot. Well, he gets pulled over, gets a ticket. Decides he's going to fight the ticket in court. So he shows up to court. How do you plead? He pled guilty with an explanation. The judge thinks, what? Guilty with an explanation? Okay, I've got to hear this. Okay, and what's your explanation? He says, well, Your Honor, apparently I did drive through a red light, at least as observed by the police officer. For you see, he was stationary with respect to the light source. And the light was red to him. I, on the other hand, was approaching the light system. Due to the Doppler shift, the wavelength shrunk, and the red light appeared green to me. The judge apparently looked down for quite some time. And then he looked back up and he said, "All right, young man, I'll make you a deal. You can either pay the standard fine for going through a red light," which is what? Haven't you gotten that ticket? How much?
Like $300.
$300, something like that. You can either pay the standard fine of $300 for driving through a red light, or you can pay the small fine of $1 per mile per hour you were over the speed limit. Now the young lad thinks about it. There was nothing on his ticket that said speeding. Which would you choose and why? If it was you, which would you choose and why?
You would pay the fine for running the red light.
I think I would pay the fine for running the red light also. Why? To have that much of a Doppler shift, he would be traveling about 1 billion miles an hour. So he just admitted to going 1 billion miles an hour by saying that he saw a green light. The judge had taken physics also. In principle, the young lad was correct. But of course, in practice, it's impossible for us to travel fast enough to see a Doppler shift like that. That's why the Doppler shift in sound is very common. People hear it all the time. The Doppler shift in light. Where see it? I must be getting excited. So, the Doppler shift in light. We may have to discuss it on Wednesday. Let me just put down the formula. F, the frequency of light that we would see, F naught, 1 minus V over C, divided by 1 plus V over C under the square root. Why does the formula look different? It's because there are relativistic effects that you and I have not discussed yet. So there is a frequency change in light, and it's given by this formula, and I will not derive this formula for you until we get into chapter 34. In chapter 34, we talk about Einstein's theory of relativity, where we can more accurately write down this formula. So for now, there is a Doppler shift in light. Here's the formula. Where does it come from? Chapter 34. You're going to have to stand by on that. V, I said here in red letters on my notes, I said, remember, V is the velocity of the source relative to the observer. And the key word underlined is relative. So, we don't ask who is stationary and who is moving. We only ask relative velocity. How fast are you approaching or receding from each other? In fact, chapter 34 makes the point that there's no such thing as an absolute velocity. There's only relative velocity. So, to set up chapter 34, I know it's a couple of weeks from now, but to set up chapter 34, I said, no, velocity is relative velocity. Yes?
If we're dealing with both of them in wavelengths, then why do we have a different formula for sound as we do for light?
All I'm going to say right now is just I'm going to answer with that one word, relativity. And I'll explain it when we get in chapter 34. Okay? So that's really what I'm doing right now, is I'm making an excuse for myself. I don't want to have to try to explain it now. I have to lay the groundwork for chapter 34 before I can do that. So my answer is stand by. About 2 weeks.
But for these ones, we just use the perspective. For these ones, we just use sound and then light.
Yeah, sound and light. Right, that's all you need to know for now. All right, it's 9:10. I'll see you today at 2:30. We're going to have a little bit of a lab today, and it'll be an easy lab for us to complete during the 3-hour period, get it written up and turned in. So it'll be due at the end of the hour today. See you then, folks.
Yep.